Part E. Evaluation and clogging problems. Evaluation of sprinkler irrigation system. Indeed, it is very important to analyze and adjust the gathering data of any established sprinkler system to be adequate to the field conditions and comfortable to the system users such as water should be applied faster than the soil integrates. Water should be applied fast enough to alleviate the losses by evaporation as possible. The amount of applied water during irrigation intervals should not be greater than can be held by the soil within the root distribution zone of planted crops. The initial system should be able to replenish the soil moisture at least equal to the peak rate of use by plants during the duty hours of system. Water should be applied as uniformly as possible over all the field area. Water losses mainly occur through wind drift and evaporation between the sprinkler nozzles and soil surface. So, losses should not be more than 5% of the system's total flow. Pipe size and its distribution should be achieving an economic balance between pipes and power costs. And water must be applied in a way that will not causing any soil erosion or damage the planted crops. Practical evaluation method. Using the gauge can method is the accurate one, which can be applied in the field under the situation conditions. Set up the gauge cans having the same inner diameter and height in a symmetrical pattern between two sprinklers across the choosing lateral. Cans should be arranged by about 1.5 meters apart where the sprinkler spacing on lateral are less than 9 meters and about 3 meters apart where the sprinkler spacing are 9 meters or more apart. Cans must be labeled aligned by numbers and inserted into the soil for about 3 cm depth to be fixed and not overturned. Measure for the pressure and discharge of the two test sprinklers at the beginning and the end time of test must be recorded. Hence, running the system until caught around 2.5 up to 3 cm depth inside the cans will not let the irrigation time be long to cause an overflow from any tank. Hence, cut off the test time, which is meaning no more spraying water fall into the can. First, measure the catching volume in each can by its number and record it in a special test figure sheet. Calculate the acclimation depth in each gauge. Divide the obtained application depth of each can by the time of irrigation. Hence, we will obtain the supplication depth per hour for each can. They record it in the test sheet under the can number, as the application can depths having the same number together. Hence, we'll obtain 20 gathering application depths from the 40 readings as illustrated in the example, as you see in the enclosed figure. Figure showing layout of spray gauge cans for evaluating irrigation efficiency. As you see, alignment gauge cans by its number and application depth per hour for each one is recorded beside. Figure showing the accumulation depth distribution on gauge area in between two laterals. As you see, calculation of minimum depth, average application depth, and distribution efficiency. Irrigation efficiency calculations. There are many mathematical calculations which must be done to evaluate the irrigation efficiency after finishing the experimental gauge can test, such as average application depth, minimum application depth, distribution efficiency, and water losses. Follow up my video by yourself. It's so easy. The rest of mathematical calculations such as application efficiency of lateral, and system efficiency. Look, my dear, and follow up. Differences on operating pressure. Determine the pressures and its differences at the whole system points are very important to calculate the system efficiency and put the stamp on the incorrect points and try to find the right solution, such as determination of the pressure in the lateral feeding lines at first sprinkler from the main or sub-main line. and at the highest point on the line and also at the end sprinkler. Measuring the pressure at the sprinkler nozzle and determination the pressure in the main line at pump station and the highest point on the line and at the first point from the pump station also. Also, mass observation moisture penetration at cross. Observation water application rate which enters the soil, especially the area around the fastest filling of gauge cans. Water applied at any spot of soil at one revolution of sprinkler to disappear before water starts to spray again on this spot. No movement of accumulation of water should be observed. Moreover, test and determination the irrigation adequacy by using a soil auger is very important also. Checking also must be done on the crop damage caused by sprinkling. Such damage may be caused by drop impact force, unfavorable jet trajectory angle, and or inadequate riser height. Evaluation of microirrigation system. Normally, water flow in microirrigation system through inlet pipes setting from the pump station within its control head and filtration system up to the last emission point in the system. Accordingly, the application efficiency of like this system depends mainly on the harmony distribution of pressure at all different locations and uniformity emission point discharged within the system. The overall application efficiency can be calculated as shown in the enclosed equation. Non-uniformity can be caused by many reasons such as variability in distribution characteristics, incompetent on either system design or user management, inefficient on pumping and or filtration system that adequate with the actual head and discharge required within the system, and outside or physical change in the system has been occurred. Emission uniformity. The normal field determination of emission uniformity is range between 85 up to 95%. It can be easily measured practically in the field by following sample views. As illustrated my dear in front of you, follow up. It is so clear and easy. The rest of calculation, the emission uniformity of lateral, submain, and for the whole irrigation system in the field as shown in the enclosed equation. Application storage efficiency. Storage efficiency is the relation between the average water stored in the root zone to the average applied water, reflects the uniformity of application. Normally, it is a coefficient smaller than 1, depending on the soil characteristics. Bezel defines the storage coefficients such as 0.87, 0.91, 0.85, and 1 for cold, sand, silt, and heavy texture soil respectively. Moreover, microirrigation has some advance on the availability of preventing the loss phenomena of water either by evaporation or deep percolation. Practically, the only right method of inspection the deep percolation under any microirrigation system is found by using time domain reflectometer apparatus TDR. Hence, deep percolation will be about 10% of the total application water. Therefore, the reasonable value of storage coefficient will range between 90 up to 95 under the ideal conditions. Wetted soil surface percent. Percentage of wetted soil surface as compared to the whole irrigation area must be sharp at 4 locations on the previous selected feeding line. Its values are related to the homogeneous and the equity of many variables such as distributed charge, spacing between the feeding lines and distributed charge, soil characteristics, interval time between irrigation, duration time of irrigation, and homogeneous of flow pressure in the whole system. Percent of wetted soil is determined by dividing the wetted soil surface by the surface area between the dust emission points as shown in the enclosed equation. Differences on operating pressure. Determine the pressure and its difference at whole system points are very important to calculate the system efficiency and put the stamp on the incorrect point and try to find the right solution, such as clear in front of you. Follow up my dear. Clogging problem and its control under pressurized irrigation system. Clogging is the most annoying problem related to the pressurized irrigation system. Partial clogging affects on the application efficiency and execution uniformity of these systems. Clogging can be caused and happened by many factors such as soil particles, lime carbonate, metallic dust, algae, precipitation of remaining fertilizer, iron slime, sulfur slime, accumulation of salts, and or plastic film. Sand and silt particles may be found in such a case from a direct source of irrigation water. Lime carbonates can be precipitation on the surface of the distributor in the micro-irrigation system as a result of evaporation processes. Anyhow, corrosion of iron, metallic pipes, and fittings in the control head, causing also of founding some metallic cracks inside the system. Sources of water as reservation pumps also encourage the founding of algae inside the system. Rest of clogging problems. Fertilizer and chemical precipitation can be found from coated materials which injected into the system through the chemication unit. Iron slime can be developed from the action of iron bacteria in water even its content is less than 1 ppm, while sulfur slime can play the same role when water contains sulfur. Moreover, plastic fillings can be found during any repairing work in the system. Generally, most of the clogging problem can be eliminated by using the suitable filtration unit, in addition to following the accuracy in installation and maintaining procedures of system as follows. Solid separation. The type of filtration unit and degree of filtration mainly depend on the source of irrigation water. By using one or more of the following methods, such as settling basins as primary sedimentation filter, screen or disc filters which is designed by mesh number, which is equal to the number of holes in a length inch, media filter, sand separator, and or foam filter. Chemical precipitation. Precipitation which causing clogging such as iron in both figures of ferrous and ferrite, forming a reddish-filling calcium carbonate and phosphorus compounds combined with calcium carbonate. There are many factors which assisting for increasing these precipitation processes, such as increasing the temperature inside the underground pipes net, as may be reaching up to 7 degrees, especially when there is no flow in the system. Changing the pressures of different gases as a result of founding an air pocket inside the system, and or increasing pH value as a result of any action. Microbiological control. Sulfur and iron slimes and sludge, which causing by sulfur and iron bacteria, successively in addition to growth of algae and other fungi, represent a biological clogging problem in microirrigation systems. Chlorination process is an effective device for controlling this problem by injection 1 ppm continually or 10 up to 20 ppm periodically inside the system through the conjugation unit. Take into consideration that flushing processes should be occur directly after this injection process. Goodbye.